Okay, YouTube, as we continue to explore functions in their function notation, we're going to be looking at solving some pretty specific equations. First one of which is the equation you can solve to find what we call the zeros of a function. And so let's go ahead and start with this. The zero of a function are all values of x for which the y value equals 0. And I say that these can be expressed algebraically as all x values for which f of x equals 0 or for which y equals 0. So one thing that we kind of want to mention here is this. Let's say we had a functional relationship here, and then I could call this curve here f of x. What we're looking for are all x values that cause this to be true. And so because we're looking for all f value or x values that cause our function to have y values of 0, really what we're looking for is all x values, okay, where our graph is at a height of 0. And so since that's the case, really what we could acknowledge here is that another name for a 0 of a function, okay, is the same as an x-intercept. So remember that when we find an x-intercept, what we're really doing is we're plugging in 0 for y, and then we're going backwards and solving for what those x values happen to be. So in this particular video, that's what I want to do. I want to get used to the fact that we often find zeros of a function, and these are the x values that cause our y values to be equal to 0. So let's go ahead and take a look at these two functions here, f of x and, well, I guess they call this one f of x as well. But what we're going to do is we're going to find the zeros of this function. So first things first, because we're looking for the x values that cause this to be true, then what we could do here is we could say, well, I know that f of x is equal to negative 2x, is equal to negative 2x plus 10. And because I want to know what are the x values that cause my y values to be 0, what we're going to do is we're just going to substitute, okay? And so this substitution we're going to make here is this. We're going to put in 0 for our y value here, and then simply put, what we're going to do is go solve for our x value. So we're going to substitute 0 for y, and then we're going to solve for x if possible. So because 0 is equal to negative 2x plus 10, let's go ahead and subtract 10 from both sides here. Suppose we'd end up with the expression negative 10 on the left equals negative 2x on the right, and then to finish this off, we'll go ahead and divide both sides by a negative 2 here. But what we end up with is the fact that x is equal to 5 here. So one thing that I want to keep in mind, and it's this, is when we plug this in, we should get a y value of 0, and that's exactly what I want to check here. So when we looked at this, we said plugging in a y value of 0, we got an x value of 5, but just to check this out, if we were to plug in f of 5, what you would get is negative 2 times 5 plus 10, which certainly is a negative 10 plus a positive 10. So again, we're looking for all x values that cause our outputs to be 0. So looking at letter B here, this is a little bit different example in that the degree of this equation is a second degree equation. It's a quadratic equation and not a first degree linear equation. So in terms of what we're going to see for x-intercepts, we may have more than one or not even one or just one. So let's take a look at this. We're going to say f of x, our function is x squared minus 5x plus 6. And we're going to substitute in for our f of x value here, we're going to put in a 0. So when we set this equal to 0, okay, we say let's go solve for x. This is different because we can't just isolate x by getting it by itself. What we need to do is solve this by method of factoring. So with equations in which you have x's to various powers, let's say, what we're going to do is we're going to try to get it all set equal to 0 and then try to factor it if we can. So I notice that this right side is a trinomial. It has 3 terms here and an a value of 1. And so since that's the case, what I'm trying to think of are there 2 values that multiply out to be a positive 6 that add up to be a negative 5. And so what I recognize is that 2 numbers that multiply out to be 6 that add up to be 5 are 2 and 3. And because they have to multiply out to be a negative 6 but add up to be a negative 5, they must both be negative here. So because it is true that x minus 2 times x minus 3 is equal to 0, then because when you multiply 2 things and you get 0, one of these had to be 0. Either a is 0 or b is 0 or both, or a equals 0 and b equals 0. Then it is the case that what we're going to do is we're going to set each of these individual factors equal to 0. So we get x minus 2 equals 0 or x minus 3 equals 0. And in either case, when we solve these here, we can just go ahead and do the inverse operations that will help us isolate x. Now we can see that 2 is the x value here and that 3 is our x value here. And so looking at these, I just want to kind of table these values here, but we get 2, 0, and 3, 0. What I want to do is go look at these graphically. So graphically speaking, just really quickly here, as we go over to Desmos, what I've done is I've graphed f of x equals negative 2x plus 10. But we can certainly see that this is our linear equation that hits at a y-intercept of 10 and has a slope of negative 2. But you can see here clearly on the graph that when x equals 5, we have an output of 0. And then for our other function here, our quadratic function, this one right here, you could see that even in the table here, when we plug in, let's see, I'll add in the 3 here. When we plug in 2 or 3, we get outputs of 0. And these are reflected in the graph by looking at the intercepts for both of the graphs. Okay, so let's see if I can close out of this here. You can see the zeros or the x-intercepts. Cheers.